Hello, everyone, and welcome to another wonderful day of symmetry. So today in PChem, we are going to be taking some of the ideas that we developed from symmetry for molecules and trying to figure out some immediate uses we can put it to. And there are indeed actually a lot of things that are well described in chemistry by symmetry. Two of the ones we're going to focus in on today are polarity and chirality. So we can end up using our symmetry to help make some real predictions about the behavior of the system, because there's going to be certain behaviors that are going to be very sensitive to essentially how symmetric a molecule is. And one of actually the first and easiest ones to kind of grasp on is electric dipoles. So most of you know this as polarity. So one of the simplest things, simplest predictions, is that if I have a molecule and it will generate a dipole. So specifically, I'm looking at an electric dipole. This is due to having one side of the molecule being more electronegative than the other side. Well, this ends up being a behavior that's at its heart rooted by an asymmetry in the molecule. There's something that's not symmetric about the molecule. So if I know something about the symmetry of a molecule, specifically its point group, I can thus figure out something about the dipole. So one of the simplest statements of this is the idea that if my molecule belongs to some point group, its dipole or its unevenness has to belong to that same point group. So let's walk through three quick examples. One of the first of which is water. So water is a C2V molecule with a rotational plane going through the axis about which the two hydrogen atoms can rotate. Well, I went ahead and did some quick calculations with Hartree-Fock, and we see the dipole also points down this same axis. So it turns out that not only the molecule will belong to C2V, but indeed so will this dipole, because it has one rotational axis, the one pointing straight down the axis, and it's also going to respond to the same two mirror planes, the one cutting along the plane of the molecule and the one bisecting the bond. None of these symmetry operations will move the dipole, and this actually should hopefully make sense, as we have this idea that since the dipole represents an unevenness of charge, that unevenness has to still can't violate any of the symmetries we've previously identified. And you can extend this idea to throwing on an extra hydrogen. So if I look at ammonia, it's going to have a dipole, again, bisecting the nitrogen-hydrogen bonds. And again, it's pointing down my threefold axis of rotation and won't be changed if I apply any of my three vertical mirror planes, each of which essentially cuts along a nitrogen-hydrogen bond. None of these symmetry operations will in any way affect my dipole. And again, this is all rooted on the idea that while this molecule may have some asymmetry leading to a dipole, because my nitrogen will be slightly more electronegative than the hydrogens, it can't be in such a way that would violate the point group it belongs to. But we can also extend this to some more messy molecules. So one possible example is 2-chloropyridine. So we went ahead and assigned this guy as a point group in our last lecture, and it belongs to the point group CS. So the CS point group only has a mirror plane cutting through the axis of the molecule. And so essentially all this limits us to is the fact that our dipole has to be pointed somewhere along the plane of the molecule. And lo and behold, it is, as I'm going to have more positive charge built up on this side and more negative charge built up on this side along the chlorine and the nitrogen. So again, this is actually a quick idea of how I can figure out the dipole of a molecule simply by knowing that it can't violate the symmetry of whatever point group I've already assigned the molecule to. And in fact, we can actually solidify what our dipole is allowed to do with a couple of quick rules. Because since I know that my dipole can't violate the symmetry group it belongs to, this means that it must obey three major rules. First of all, my dipole can't be pointed perpendicular to the axis of rotation. So this is our principal axis of rotation. Though to be fair, this can actually apply to any axis of rotation. So in these two molecules, they have a single axis of rotation. For water, it's pointed along the dipole. And so essentially what this says is that I can't have a dipole that's pointed at a right angle in this direction or this direction. And the same thing with my ammonia. Again, I can't have a dipole that's pointed pretty much any way away from this main axis of rotation. Similarly, we also have that the electric dipole can't be pointed perpendicular to a mirror plane. So for water, we have two mirror planes, one cutting essentially in the plane of the screen and one bisecting this bond. And you'll notice that that this dipole is pointed along both of these planes. It can't be pointed, say, straight towards us from the oxygen, because that would be perpendicular to the plane of the screen. Similarly, it can't be pointed in this direction because I have a mirror plane bisecting this axis. So this severely limits where I'm allowed to have a dipole present. And we also see this when we're looking at chlorobenzene, as I have a mirror plane along the plane of the molecule. So I can't have the dipole pointed anywhere away from the plane of the molecule. So these are some quick rules that more or less confirm what we already found, that the dipole has to belong to the same point group as the molecule itself. And finally, we also have that if I have an inversion center, any inversion center at all, I can't have an electric dipole. And this would be because if I have a center of inversion, say think of benzene, then I have everything is symmetric on any side of the molecule. So there's no way I can move my dipole. So if I try to invert my dipole around any inversion center, it will always end up pointing in a different direction. So as long as you can identify an inversion center, this means that my molecule will be nonpolar. And so as a result, it turns out the most highly symmetric molecules, so those that contain a lot of symmetry elements, are generally going to be nonpolar simply because they can't form a permanent dipole. The permanent dipole will violate some rule. And so essentially, as more symmetry elements are present, one of these elements is going to be very likely to forbid a dipole from forming. So let's go ahead and look at our old friend, PF5, so phosphorus pentafluoride, which belongs to D3H symmetry. And in this case, we have mirror planes that cut along the plane of these three fluorines, as well as ones that bisect or that cut along these three fluorines, and these three fluorines. So one of the issues is that when I start having so many different mirror planes, I'm likely going to end up, I can't point a dipole in any direction without being perpendicular to somebody. And the same thing holds with the number of n-fold rotations I have, because I have a three-fold rotation along this main axis, and then three more two-fold rotations along this axis, and this axis. So again, the dipole would be perpendicular to somebody. So the more symmetry elements you have, the much less likely you are going to be able to maintain a dipole. And again, we can also think about this the reverse direction. The more symmetric my molecule, the more resistant it is, the less likely I'm going to have an imbalance of electronegativity or charge. And so as a consequence, it turns out that very few point groups can actually support polar molecules. In fact, the only ones that can actually form any sort of polar molecule are going to be CN, where pretty much all you have is an n-fold rotation, CNV, where you have an n-fold rotation and a set of mirror planes that run in the same direction as that n-fold rotation, and CS, at which point all I have is a single mirror plane. So if you do not belong to one of these 3 point groups, congratulations, it turns out you are nonpolar. So as a consequence, we can see something like ammonia. It has C3V symmetry. So it can indeed be polar. Whereas something, as soon as you see a D or as soon as you see an H, this indicates you're too high symmetry to maintain a polar molecule. So this is a quick way of just running through your point groups and then not actually having to worry any further about, is this polar, is this not polar? Now, one of the additional tricks we can apply is if you do have the point group, and especially if you have an n-fold rotation, it turns out that the electric dipole has to be pointed along the n-fold rotation. So for something like ammonia, we have our n-fold rotation pointing in this plane. Well, it turns out that because of that, this will also be my dipole. And then all you need to do is use your chemical intuition to say which side is more electronegative and which is less. In this case, nitrogen is more electronegative, so I'll have more negative charge over here, more positive charge on this end. So without having to do any fancy computer programs and just using point groups, you can usually quickly identify your electric dipole and its direction. All you need to do from there is figure out the magnitude. And oftentimes, we don't even need that. So just by identifying the point group of a molecule, you can quickly identify at least a lot about its electric behavior, because polarity does drive a lot of reactivity trends. But there's also one other classic molecular behavior that is at its heart all about symmetry. And this is your old nemesis from OChem, chirality. So we can also, not too surprisingly, use symmetry to determine whether a molecule is chiral or achiral. And again, just as a reminder, a molecule is chiral if it has a non-superimposable mirror image. So there's a different way to construct the molecule that still generates a mirror image without being able to superimpose the two. So we can actually identify something about the chirality of a molecule using a simple rule from our book, which is a molecule may be chiral only if it does not possess an axis of improper rotation. So this is that SN axis we brought up earlier. Now, I personally am not a big fan of double negatives. So let's reword this one a little bit. A molecule must be achiral if it does possess an improper rotation. So if I can identify an axis of improper rotation, so if the molecule has an SN symmetry element or SN symmetry operation, then congratulations, I know that it has to be achiral. And one of the ways we can think about why this has to be the case is, again, chirality is supposed to be a molecule is going to be achiral if it has a superimposable mirror image. So a way to think about this is that when I'm looking at SN symmetry, the idea is I take a mirror image and then I will do a rotation to try and get the same point back. So, or alternatively, you can think about this as moving it and then sending the point across. And if it's identical after a rotation and a mirror image, this is more or less what we're talking about when we're talking about chirality. I take a mirror image and then I do some sort of rotation or finagling to make it so that I can superimpose the two molecules. Now, it is worth noting that if a molecule does not possess an axis of improper rotation, doesn't mean that it's chiral. There may be some other way to superimpose the mirror image besides a rotation. But very frequently, rotation is the easiest way to try and superimpose two mirror images. So the major problem about this is that while being able to identify an improper rotation is a huge hand of identifying something if something's achiral, it turns out that at least for me, that an improper rotation is the hardest of these symmetry elements to try and identify. So instead of trying to identify if there's any improper rotation, we often like looking to see if there is one of the special cases of improper rotation. So a symmetry element that's a little easier to spot. So one of the special cases is an inversion center. So if I take a point, I send it through an inversion center, and there's an identical point on the opposite side. Well, it turns out this is the same thing as an S2 improper rotation, because in that case, I rotate the molecule, the point 180 degrees, and then send it across an axis. This will actually get me to the same exact point as if I do an inversion. So if there is an inversion center present in your molecule, congratulations, you also have an improper rotation. But there's actually a much more common improper rotation that we don't often think about. Sorry about that. And that's the mirror plane. So if I have a mirror plane, there's an identical point on the opposite side of a mirror plane. This is going to be the same thing as an S1 symmetry operation. I rotate the point 360 degrees and then impose it across a mirror plane. So it turns out if any symmetry group, if any point group possesses a mirror plane, which is, by the way, a lot of them, it means that it is, by definition, an achiral point group. And again, this can be very useful because these are actually fairly common symmetry elements of a lot of point groups. So while this might not help you quickly assess chirality, it can definitely be a huge advantage in assessing achirality. So here's some essentially quick tricks that we can use to identify some behaviors of a molecule, both polarity and achirality, simply by knowing what point group a molecule belongs to. So this is one of the reasons why people are often very enthusiastic about symmetry. However, it turns out that we can start to develop a more systematic description and use of point groups that will really help us assess the behavior of electronics and specifically molecular orbitals, which we'll go ahead and start next time as we begin group theory. Till then, take care and stay healthy.